but in most applications, it's very small. So the Tresca will be very good for metals, but not for geomaterials. But now, what we have is not a line or a combination of lines. Now we have, and of course, you know, these are sides that go inside the hexagon. Now this is a failure surface, okay? And I think my drawing is reasonably okay, so I don't need to show something in the computer. But we went from 1 dimension to 2 dimensions, now to 3 dimensions. Now we plot the state of stress in here. The Tresca criterion is going to say that you cannot be outside this failure surface, because if you're outside, you are in failure. There is a problem, though, with this Tresca criterion. Do you see any issues with this Tresca criterion? Well, that's one of the bad things about the Tresca criterion, but there is another one. It's mostly a mathematical problem. Sharp edges. So these sharp edges, we're going to see later that we want to take derivatives around that failure surface. And we take derivatives around that surface. When we get to this point, you have two derivatives, right? So which it's not very convenient. So in order to solve that problem is that we have the von Mises criterion. And the von Mises stress failure criterion is not defined in terms of principal stresses, but it's defined on terms of J2 and I1. And basically, what von Mises says is that, okay, you know, it's I don't care what are the difference between the principal stresses, but just compute J2, in which we know that J2 is this equation I'm writing right now, summation of the difference of the principal stresses times 1/6. Von Mises says, okay, just compute that one, and the limit of the J, I'm going to fix a limit of J2, and that's it. So the stress, the J2 cannot go beyond a predetermined value. And in this case, this value, that value is called K. And let's try to find a physical meaning for that and to compare it with the Tresca criterion. If you were to do, for example, a test in which you get to the shear yield or to the stress yield into sigma 1 and sigma 2 is equal to sigma 3 and equal to 0, as in a typical tension experiment, then J2 will be 1/6. This is going to be 0, and this is going to be 2 sigma 1 squares, right? So 2 sigma 1 squares, that's 1/3. So the maximum J2, or square root of J2, as we have it over here, is going to be sigma y divided square root of 3. And that's it. So you perform the typical tension or compression test, but this is mostly valid for metal, so you will do tension. And you will say, okay, my maximum J2 is going to be this value, and this is also the value that we're plotting over there is K. So as long as your square root of J2 does not go above that value, then you're fine. If you're at the point or where it gets over there, then you are at a failure. So very simple, right? But let's see how that works in the three-dimensional principal space. So what do you think that is going to look like? What?
So with the last one was the hexagonal prism around the equal stress axis, so it's going to be like a tube.
Okay, so if this is a regular hexagon, right? The one of the Tresca. So if you were to draw the von Mises criterion, it's going to be a circle that circumscribes the hexagon. But it's going to be a perfect circle. And now your surface is not an hexagonal prism, but now it's a cylinder, where the radius of the cylinder, let's say this is the center O of the principal stresses. The point in the hydrostatic axis is P, and the particular point on the circle is N. This is just geometry. Actually, yesterday I was playing like an hour with this problem because I couldn't figure out the right equations, but finally I did. But it's just geometry. The distance from P to N, that's going to be equal to the radius of the circle, and according to the von Mises criterion, that's going to be the square root of 2/3 times the yield stress. That's the maximum radius that you can have, or well, actually that's the radius of the cylinder. And also the distance from O to P is going to be sigma m, the mean stress, divided square root of 3. And in general, if Pn is, now we're considering that's the radius of the circle, right? But if you were to decompose that into a location which is not exactly at the shear limit, let me call it Pn prime, where n prime is, say, somewhere in between n and p. This is going to be equal to a square root of 2 times square root of J2. So remember that, well, I forgot to say what this plane is. So we said that this guy, this is the hydrostatic axis, and perpendicular to the hydrostatic axis, we're going to have this plane, and that plane is called the deviatoric plane, or some other people also call it the octahedral plane, but I like more deviatoric plane. So it's a plane which is perpendicular to the hydrostatic axis, and any state of stress also you can write in terms of OP as a term of I1 invariant, and as in terms of J2 the second invariant of the deviatoric stress tensor. All right. Okay, guys, I think I went a little bit over the time. So, so far we consider just stress insensitive materials. We're going to extend this same thing to stress sensitive materials on Thursday.